So it's time to develop some shortcuts or formulas for calculating the derivative more quickly than always having to resort to the definition of the derivative. Because at the moment, that's exactly what we have to do. Every time we want to do the derivative of a function, we have to apply this definition. So let's look at some different categories of functions and apply this formula and see if we can come up with some general rules along the way. So the first situation we're going to look at is the derivative of a constant. So if you've got a function y equals c, where c is a real number, so that might be my function y equals c. And if I just think about this, if I think about drawing the derivative graph, the slope of the tangent line at any point I know is 0. It means my derivative is 0. Alright, so intuitively that makes sense, but in order to prove this definitively, we need to apply a proof which involves applying our definition of the derivative. So here we go. The derivative of y equals c would be the limit as h approaches 0 of f of x plus h. Well, there's no x in this formula, so f of x plus h would just be c, minus f of x, which is c. The y value is always c. It's a constant function, over h, which means the limit is 0 over h, which is 0. And the limit of a constant we know is 0. So in fact, we have shown that the derivative of a constant is always 0. And now that we've proven that, we can use that result whenever that particular situation comes up. Another common type of situation that comes up is a power. So if you have y equals x squared or y equals x cubed, you may want to do the derivative of that. So let's take this general situation and see if we can come up with a general formula for the derivative of a power. If I apply my definition of the derivative, as I always have to, the derivative of x to the n by my definition of a limit would be limit as h approaches 0, f of x plus h, so I'm going to put x plus h in for x in my original function, minus f of x, which is x to the n, all divided by h. Now we need to work this limit out, and when you look at this you might say, how the heck am I going to deal with that? X plus h to the n. So let's just put this on hold for a second, and let's just look at some of the expansions of a binomial a plus b to various powers. You've done a plus b squared often, and you know that that's a squared plus 2ab plus b squared. And to get subsequent expansions, you would need to take the previous one multiplied by another a plus b to get, as you see, these have all been worked out for us. And what I want you just to do for a minute is just to take a look at some of the patterns involved in these expansions. Here's a couple of things to notice. When it's a plus b squared, there's 3 terms. It's a plus b cubed, there's 4 terms. So there's one more term in the expansion than there is exponent on the power of the binomial. You'll also notice that the powers of a start at the exponent of the binomial, and they decrease from term to term. So we have, for example, a to the 4th, a to the 3rd, a to the 2nd, a to the 1. The last term can be thought of as having an a to the 0, whereas the powers of b increase, b to the 0, b to the 1, b to the 2, b to the 3, b to the 4. You'll notice that the coefficients of the terms, front and back, are the same. Second and second last are the same, and so on. There's a symmetry to those coefficients. But most importantly, I want you to notice that the second coefficient in the expansion is the same as the power on the binomial. So just to be sure that we're getting the hang of some of the patterns that are happening here, let's just do the expansion of a plus b to the 6th. So I would have 7 terms in the expansion. The first term would be a to the 6th. The second term would be coefficients the same as the power up above here. So it'd be 6a to the 5th, b to the 1. And then there would be some number after that. Now, we don't really know what that's going to be, so let's just use a capital letter here, n. It'll be something, a to the 4th, b to the 2nd. And then there'll be something, a to the 3rd, b to the 3rd. And then there will be the coefficient after that's going to match the third coefficient, because this is going to be the third last term. The second last term is going to have the same coefficient as the second term. And the last term would be b to the 6th. Alright, so when it comes down to my question about x plus h to the n, let's apply our patterns above to this, doing an expansion of this. If my exponent is n, I know I'm going to have n plus 1 terms in this expansion. So the first term is going to be x to the n. The second term is going to be the coefficient. The coefficient is going to be the power on the binomial n. It's going to be x to the n minus 1, h to the 1. And then we're going to have some other coefficient, which we're not sure about, so I'm just going to call this capital M. X to the n minus 2, h to the 2. And this pattern is going to keep going. And the second last term would be nx h to the n minus 1. And the last term would be h to the n. Now this expansion is what has to go into this part of my evaluating of the limit. So let's put all of this together. Alright, so here it is all put together. Limit h approaches 0 of x plus h to the n, which is all that, minus x to the n, which is that, all over h. So the first thing you're going to notice that happens is that the x to the n's cancel out. The next thing we would typically do is we would factor out an h, so that's exactly what we're going to do. Now you'll notice that each of these terms is going to have an h in them, and so when I factor the h out, the only term that won't have an h will be this one right here. Okay, so I'm just working my way down. If I factor an h out of that, that's going to be nx h to the n minus 2 plus h n minus 1 all over h. And those cancel out. So now I'm ready to evaluate my limit. As h approaches 0, all of these terms over here, these are all going to go to 0 except this particular one. And so I've got the derivative of my power being nx to the n minus 1. I've got a nice formula for doing the derivative of a power. And here's how nicely it works. If I have the derivative of x squared, my power would be 2x to the 2 minus 1. So 2x. If my power was x to the 7th, then my derivative would be 7x to the 7 minus 1. 6. I can very quickly get the derivative. This is what we call the power rule. And we can use it for a variety of things. We can use it for powers, for radicals. So what if I had the cube root of x? I could write my cube root as x to the 1/3. And then applying my power rule, it would be the power 1/3 x to the 1/3 minus 1, which would be 1/3 x to the negative 2/3. Alright, and you could return that to radical form if you needed to or wanted to, which is 1/3 times 1 over x to the 2/3, which would be 1 over 3, the cube root of x squared. you could use the power rule to do something like the derivative of 1 over x to the 5th. Because you could write that as x to the negative 5. And then applying the power rule, it's n times x to drop the exponent by 1, negative 6. So the derivative would be so. Alright, another common situation is us needing to do the derivative of a sum or a difference. So we have a function made up of 2 or 3 or more other functions, f of x plus g of x in this case. So I'm going to apply my formula above. What I'm doing is I'm considering this whole thing my big F of x. Big F of x is made up of the sum of little f and little g. So let's apply this to this formula here. So big F of x plus h would mean plug x plus h wherever I see x. So that would become this entire piece here. This is big F of x plus h minus the function itself, big F of x, all divided by h. Alright, now what I'm going to do is I'm going to reorganize this part right here. So all I've done here, going from this step to this step, is reorder the terms for my convenience to that plus that. Now you can perhaps see why I'm doing this. I can then take the limit of these two parts. The limit of a sum we know is the sum of the limits. So the derivative of f plus g I can see is coming down to the derivative of f plus the derivative of g. The derivative of a sum is the sum of the two derivatives. And in fact, the same is true for subtraction. Okay, so I could just add that on. Alright, and final relationship for now. We're going to take a constant times a function, where c is a real number, and we're going to do the derivative of that. So c times f of x would be, applying my definition of the derivative, on the top I could factor out c. I could then break my limit above up as so. I know the limit of a constant is a constant, and I know that this limit is f prime of x. And so the derivative of a constant times a function is the constant times the derivative of the function. So just to do some quick examples of applying the last two properties in coordination with the power rule and the derivative of a constant. That's the derivative of a sum and a difference, and so I can do the derivative of each term separately. Furthermore, when I have a constant in front, I can think of the constant as just coming outside of the derivative. Okay, now I don't have to show those steps every time I do it. I'm just trying to show you how all of the properties come together and we are able to do the derivative of a more complex function. So here's my power rule, which is the exponent x to 1 less than the exponent. So that's 7 times the derivative of x squared, which would be 2x. The derivative of x, that would just be 1. And the derivative of a constant is 0. And so my derivative for this function is 3x squared plus 14x minus 3. Alright, one last example. The derivative of this function, which looks a little bit more complicated. But what I could do here is I could think of this as just being, and since I have a constant times a function, I can pull the constant outside. So I know that the derivative is going to be 1/19 times the derivative of this function, which is the derivative of a difference involving the power rule within it. So that would be 28x minus 21, and so that's my derivative, written nicely like so.